Hi and welcome back. Let's look at deleting nodes from a binary tree when they have two children. So when the toDelete node has two children, we must do something a bit special. Let me bring up my diagram once again. We've looked at this before, just a quick recap. Let's say we want to delete the node 9. What we must do is find the rightmost node in the left branch, so 8, or, if you prefer, the leftmost node in the right branch, 11. Because we've coded a find rightmost, we're going to stick to that. We're going to use 8 in this case, but you can use 11 if you prefer. So we're going to find the rightmost node in the left branch. We will also need its parent, because the parent will have to point to the children. Okay? Something that we know is that the rightmost node in this branch has nothing to its right. Okay, hopefully that makes sense. The rightmost node in this branch doesn't have anything to its right, because if it did, that would be the rightmost. So when you go as far right as you can, this node has either 0 or 1 children, not 2. Okay? So that is important because as part of deleting 9, we are going to have to delete 8, essentially. We're going to move 8 up here, which means that 7 has to point down here. Like that. So essentially we've deleted 8, and if 8 had 2 children, this would get extremely complicated. Because we'd be deleting a node of 2 children by deleting another node of 2 children. This is quite simple. If 7.5 had other children, this would be fine, because 7 points to 7.5, 7.5 children stay there. So that's okay. And of course, if 8 has no children, then that's fine. We don't have to worry about it. So no problem. Let's start with this scenario. The scenario where we want to delete, say, 9, and that has a node in this structure here. So the first thing we have to do is see whether the node we want to delete is at the left or at the right of its parent. Okay? So if toDelete equal toDelete parent left, let's say. I'm going to delete this pass, by the way. Elif toDelete is equal to toDelete parent right. And of course, else, what happens when they're the same? When you want to delete the root and it has 2 children. Now, for all of these, we're going to need the rightmost node in the left branch. So we're going to say rightmost equal self.find rightmost of toDelete left. Okay. And rightmost parent is going to be self.find parent of the rightmost's value. Once again, find parent, which is up here, takes in a value and sort of goes to the tree and tells us what the parent is of the value we're looking for. So here we've got the rightmost node in the left branch, and we've also got the rightmost parent of that node. We know that it is a rightmost node because there is a left branch. toDelete left returned true, or it wasn't none, so we know that this is not going to be none. So therefore this is fine. Accessing rightmost value like that without checking or without catching any exceptions is okay, because rightmost value will return something. We know that because we have 2 children. Okay? Now, if we want to delete something on the left, what do we have to do? Let's go back to the diagram. Let's say we want to delete, let's start with the right one. Let's say we want to delete 9. So the first thing we have to do is find out 8, which we've done that. We've done the rightmost node. Then we have to say the rightmost node's right now has to be equal to 12, right? If 8 is going to replace 9, 8's right must be what used to be 9's right. Let's start with that. Rightmost right has to be equal to toDelete right. Okay? So that means that the rightmost node here, 8, is going to replace 9 by pointing at 12. The toDelete's parent now no longer has to point at 9. It has to point at 8. So toDelete's parent has to point to the rightmost node. Let's do that. toDelete parent right equal rightmost. And by the way, I apologize profusely. We said we were going to do the right first, so that's there. If you wanted to do the left, it would be exactly the same, but this would be in the left. Okay. So we found that the rightmost node's right must point to what used to be the toDelete's right. So 8 is going to point to 12. toDelete parent right has to point to 8 because toDelete is equal to toDelete's right. So we're deleting 9, therefore the parent's right has to point somewhere else. If we had another 2-child node here on the left, it would be this left that has to point somewhere else. So that is what this is doing. Okay, hopefully that makes sense. Finally, if we are deleting this one, and if we are deleting the head, we're going to find the rightmost node again in the left subtree, which is going to be 5. And what we have to do is say the rightmost node's right must be 9, which is, again, this line here. But now, toDelete parent equals rightmost. This is sort of correct, but toDelete parent is toDelete. So it's the same node because they're both the head. So what we'll do is self the head is rightmost. Okay? So if we want to delete this one, the head must become the rightmost node. That's the 5. So the 5 would move up to here. Hopefully this makes a little bit of sense. There is, however, one more thing that we have to think about. Let's run again through our algorithm for deleting the nodes. Notice how we've not used the rightmost parent, by the way. That's really the problem. Let's imagine we're trying to delete 9. So toDelete is the parent's right. So this is correct. The first thing we're doing is we're finding the rightmost node and setting its right to be the toDelete right. So essentially moving this 12 down to the 8, like that. This is correct. If we want to move the 8 up here, that's what it has to do. Then we're setting the parent, toDelete parent, right to be the rightmost node. And as you can see, there is something that's a little bit off, which is that we've deleted the 9, but we've also deleted the 7, because nothing's pointing to the 7. So we have to fix this. What we have to do is say 8 left must point to 7. 7's right must point to 8's left. Okay? So, what we have to do is rightmost parent dot right equal rightmost dot left, and then rightmost dot left equal toDelete dot left. Okay, now once again we're going to go through this algorithm. We're going to change the others in just a moment. The first thing we're doing is setting rightmost parent's right, so that's this guy, equal to rightmost left. Oh, sorry, rightmost parent is this guy, 7. 7's right is going to be now 7.5. Okay. The rightmost left is now going to be toDelete's left, so 7. So the 8 is now going to point to 7. The rightmost's right is going to point to toDelete's right. And toDelete parent's right is going to point to the rightmost node. Now, as you can see, this is a bit convoluted. I'm just going to move it in a moment. It's going to make sense. Nothing is pointing to 9. So we can delete it. These arrows we can delete. We can move the 8 up here. Does that make sense? I hope so. So these 4 steps get us to this position. Of course, this one is here to the right. I'm going to undo these changes just because we have still one more scenario to go through, unfortunately. Sorry, you did not see that. This is for the next bit. And we also need these bits of code here in the other parts as well. Okay, so this is needed in all occasions. So, we have one more scenario. Let me show it to you. We have this scenario here. So I'm going to copy this, then I'm going to do this, then I'm going to delete it, I'm going to paste it in here. This is another scenario that we have to think about. What I'm going to do is I'm just going to modify it slightly. I'm going to add another node here, let's say 6.5. That's going to be to the left of 7, of course. So we have this scenario here. 9 is the node we want to delete. 7 is the rightmost node. It's got nothing to its right. 9 is also the rightmost parent, because 7 is the rightmost, therefore the parent is 9. 6 is still to delete parent. Let's try to delete 9 using our little algorithm. First, the rightmost parent's right is going to be the rightmost's left. Okay, so this guy is going to point to 6.5. This is what we're doing here. Rightmost parent, 9, is the rightmost left, 6.5. Then we're saying rightmost left is to delete left, which this makes very little sense because it is going to point to itself. Rightmost right is to delete right. Okay, so finally something that makes a little bit of sense. This is okay, we want to do that. Finally, to delete parent's right is the rightmost. Nothing points to 9, we get rid of all of them. But also, we've accidentally deleted 6.5. And 7 points to itself, which is not ideal either. We're going to get into many infinite loops if we do that. We don't want to do that. So, how do we do this? Well, it's actually pretty simple. The whole problem in this scenario is that toDelete is equal to the rightmost parent. And then we're sort of setting some properties that we have to move around from toDelete and rightmost parent, like say these, that we just cannot do because they are the same thing. When they are the same thing, the only thing we have to do is get the rightmost's right node and make it 12. And get 6 and point it to 7. This is all we have to do when they are the same. Now nothing points to 9, and 7 becomes the one we wanted. Yeah. So as you can see, maybe that was a bit too fast. All we have to do is rightmost right, which is 7's right, equal to delete right. And to delete parent's right is the rightmost. So we only want to do these two lines. That means we need these two for when they are not the same. So if rightmost parent is not equal to toDelete, run these two lines. Okay, if rightmost parent is not equal to toDelete, run those two lines. And down here, if rightmost parent is not equal to toDelete, run those two lines. Notice how we've got our if statements here, and these blocks of code are always the same in all if statements, so we can just extract them. Okay, we can just remove them from the if statements there and move them up here. Similarly, rightmost right is to delete right. This can also be extracted and put here. And this now becomes a little bit simpler. So once again, going back to our diagram, I'm going to just delete. Well, actually, let's not delete those clowns just yet. let's say once again we want to delete 9. So we've got our little algorithm. We find the rightmost node, which is 7. We find the rightmost parent, which is 9. Is the node we want to delete equal to the rightmost parent? Yes. So we jump straight through this if statement and into here. The rightmost right node, this one down here, which doesn't exist yet, is going to be toDelete right. Now, is toDelete the parent's left? No. Is it the parent's right? Yes. So we point that there. That's all we need. Now let's go back to having something like an 8 here. Now the rightmost node becomes the 8. The rightmost parent becomes the 7. toDelete becomes 9. toDelete parents is 6. Okay, so this is our other scenario. And what we want to do is, once again, we want to delete 9, find 8, find 7 as rightmost parent. Is rightmost parent equal to toDelete? No. So we go into this if statement. Rightmost parent right must equal to the rightmost's left. And by the way, we'll just add this 7.5 back here. 7.6, that's okay. So the rightmost parent's right must equal the rightmost's left. So it has to point to 7.6. The rightmost's left must equal toDelete's left. So this 8 here must now point to 7. The rightmost's right, this guy was the rightmost, the right must point to toDelete's right. So down here. And finally, because 9 is at the right of the parent, 6 must point on the right to the rightmost node, which is 8. Then we can delete 9, move 8 up here, and we got it. We got exactly what we wanted. Now, this is an extreme mind-boggling algorithm, at least when you're starting, and I would not expect you to sort of grasp it immediately. And again, draw this out on paper. Don't feel bad for drawing it out. Everybody draws it out. I have many drawings of this stuff, and even with these diagrams, I can see that it's not so obvious to understand. And especially when you have 100 lines of code, well, not 100, but sort of 50 lines of code to delete a node in a data structure, you know that it's pretty complicated. Hopefully this helps though. It can pop up in interviews, it can pop up in coding challenges. It's sort of a good thing to know in general for when you're dealing with databases and data that you have to search through very quickly and so forth. And generally, just knowing about binary trees and that they exist and, a little bit of a notion on how to use them is going to make you a more well-rounded developer. But I've never had to use them in my day-to-day job. So take it, understand it, know it's there. Don't feel like you have to remember this algorithm line by line, because you don't have to. And you can always come back to the course and watch the video again if you need to. So that's it for this video. Hopefully this helps, and I'll see you on the next one.